Found this problem in a book published in 1970 by a Polish gentleman by the name of Sierpinski. And he worded the problem, that's what, 55 years ago. And he worded the problem like this. He says, find all positive integers a for which a to the 10th plus 1 is divisible by 10. That's how they did it back then. I think the modular arithmetic approach is a better way to do it. This statement right here, a to the 10th plus 1 is congruent to 0 mod 10, turns it into an equation type of structure where it's easier to manipulate. You can work it directly the way he did this all the way back in 1970, but in my opinion, the modular arithmetic approach is better because it lends itself to equation manipulation. The name of the book is Sierpinski's 250 number theory problems, and again, published in 1970 in Poland. Now, one thing I want to talk about, this deals a lot, this particular problem deals a lot with what they call last digit analysis. So let me give you an example of what I mean, modulo 10. 78 is congruent to 8 modulo 10. So this is an equivalent way to characterize what we mean by the last digit. It's visibly manifest. 78 has a last digit of 8. Or this is mod 10, sorry, mod 10. And another way of thinking of this is 78 minus 8 is a multiple of 10, namely 70. 78 minus 8 equals to 10 times 7. Okay. Now you don't always have to think of it like this, but that's why these numbers are the same in the modulo 10. 78 and 8 are the same modulo 10. Okay, now, so let's keep that in mind as we move along. Now, after you trust this statement right here is fairly easy to, we're looking for all integers, positive integers a, such that a to the 10th is congruent to 9. And that's just because of the simple fact a to the 10th plus 1 is congruent to 10. But 10, of course, is 0 mod 10. So it's easier, in my opinion, just to search for these rather than always have to think about adding the 1 when you're actually doing it. Now, if you go along and take a look, well, I tell you what, first of all, there's some obvious things that are based on this result right here. We're seeking all a such that a to the 10th is congruent to 9. Notice that all the even numbers, let's just write them in a list. 2 to the 10th, comma 4 to the 10th. There's no way they're going to leave a remainder of 9 when you divide by 10, right? And the same with 5. 5 to the 10th. Because 5 raised to any power ends in 5. The same with 6. 6 raised to any power ends in 6. We know that just from common experience. And then what else? 8 to the 10th. None of these can be congruent. And I'm going to do the negation, the slash. That's universal for negate. None of these could be congruent to 9. And that's manifest. You don't have to spend too much time on that, right, folks? If you raise any of these numbers, 2, 4, 5, 6, or 8 to the 10th power, no matter, there's no way that's going to end in 9, okay? So we really don't have to worry about those as possible solutions. We don't have to worry about 2, 4, 5, 6, 8. So that eliminates quite a bit from the very beginning, okay? Now, so from this point on, all we have to do is just consider the numbers 3, 7, and 9. Those are the only ones that are excluded from the list I just gave you, 3, 7, and 9. Now, you guys are familiar with the Euler Totient Function. Phi of 10 is equal to 4 because there's exactly 4 numbers that are relatively prime to 10, namely 2, 3, 7, and 9. Okay? And you can read up on the theory on this, but this is a very, very convenient result because for 3, 7, and 9, we have this convenient a to the 4th is 1, right? So that means that a to the 10th is going to be congruent to a squared. See, a to the 4th is 1, 1 squared is 1. And so you get a to the 10th is congruent to a squared mod 10. And checking down here, we see the only two numbers in the list that work are 3 and 7, okay? Notice that 9, when you square it, would end in 1, right? Okay, so 3 and 7 are our solutions in the reduced residue class, but the more general solution would be a equals to 3 plus some multiple of, call it K1, K sub 1. Remember, 10K sub 1 is congruent to 0 mod 10 trivially. And also in a similar fashion, A could be equal to 7 plus 10K sub 2. And I don't know how important it is to use different constants. I think it's pretty clear they wouldn't necessarily be the same constant, so it's probably better to distinguish. But these are the solutions. So a number like 13, for example, would work. 23. Not just 3, but a whole equivalence class. 3, 13, 23, 33. Right here you would have, just so on. Okay. And right here you would have, 17 also, 27, and so on. So there are an infinite number of solutions of these forms. Okay, and I don't know if you're still alive, Mr. Sierpinski, but I'd like to know if you agree with the fact that the modular arithmetic approach is a little more organized as far as solving these problems. All right. Thank you for viewing.